So let's get started again. I will introduce these classes of operators for you. And again, like the space, L2 is something that will follow us the rest of the course. Also, the three operators I will define now will follow us the rest of the course. So we will define a translation operator, which is something that you'll think you have seen that before. Then we will define a modulation operator, which you might first think you have not seen before, but then I'll remind you that we have actually seen it. And then we'll define a dilation operator or scaling operator, which is something new, but nevertheless, I think this is an operator that you'll consider natural as well. So we look at three classes of operators. And actually, for all three of them, you can define them on arbitrary LP spaces, but we will just look at them for the moment on L2 of R. From time to time, we will look at the same operators on some other spaces, mainly at the problem session. You'll get some exercises where you just check how these operators work on other spaces. So the first one of them is the so-called translation operator. So we have to introduce a certain parameter. So we say that for some real number A, we consider the translation operator and this is something we will denote with a T, and then we put an index A because it depends on which value A we have chosen. So for each A, TA will be an operator, and it is supposed to go from L2 of R into L2 of R. And the way it acts on a certain function is that if you take the operator TA and we apply it to the function f, so that means we put in a function that belongs to L2 of R, then a new function in L2 of R comes out. That means we want TA of f to be another function in L2. That means we need to tell what should be the value of this function in a point x. And the way this is defined is to say the function value of TAF in the point x, this should simply be f evaluated at the point x minus a. So you can see what the operator does. It takes the function which is here, and then it just moves it to one side or move it to another side, depending on the sign of the number a. The second operator is again defined for a certain parameter, now we call it B. So we define the so-called modulation operator. So we denote this operator by E, and then again with an index B, and this should be an operator going from L2 of R into L2 of R. And again, we have to say what should be the value of EB applied to a function f evaluated at a point x. And the way we define this is that we have to multiply with a certain exponential factor, namely e to the 2 pi I b x. We take this factor and we multiply it on the function f. First, when you look at this, you might say, why do we want to consider that operator? But if you think a little bit back to what most of you did at the course Mathematics 2, then you will know that these exponential functions, e to the 2 pi I bx, they play a very important role in Fourier series. Because, you know, Fourier series on complex form, they are formed exactly by looking at functions of this type, where the parameter b is then something that you just call k, and k is something that runs through all the integers. So the functions in the complex exponential Fourier series are exactly the functions of this type, where the parameter we have here takes the values 0, plus minus 1, plus minus 2, plus minus 3, and so on. Then you might say, okay, now we don't have just the complex exponential functions, because we are multiplying with the function f of x. But if you, as function f, if you take the characteristic function just for the interval minus pi to pi, what you get out here is exactly these functions on the interval from minus pi to pi, and then 0 outside. And that means for this particular choice of your function f, you get exactly the functions that give you the basic for Fourier series. So you see, to consider these operators is very close to what we already did in Mathematics 2. Let me define the third class of operators. And here there's a slight difference, because you can see A and B are arbitrary real numbers. Now we look at a parameter c, and we are not allowed to take c equal to 0. We will actually just look at c that are greater than 0. So for c greater than 0, we define the dilation operator. So the name for that is d, and then with index c. Again, this is an operator from L2 into L2 of R. And the way it works on a function f is that it gives us the function value 1 divided by square root of c. Here you see the reason that we want c to be positive, and then f of x divided by c. So you can see, depending on which value of c you take, you actually get some scaled versions of your function f. I could make some pictures, but they will not look very nice, so instead I will show them to you. So actually, all of these operators, we can make a draft of them, except the modulation operator. We have to be a little bit careful with this. It's not so easy to make a draft of this because of this complex factor we have in front of this. But let's look at the first operator, the translation operator, and the dilation operator. So what we do here is we consider this function as starting point. Then the first operator we are dealing with, the translation operator, which just replaces f by f of x minus a. You can see this will just take the function and it will move it around on the axis. So this is what you see here. Here we start with the function f, and then what we have here is a translate version of the function. So it's exactly the same function, it is just shifted. Somehow this corresponds to, we might have a certain signal corresponding to an experiment that starts at a certain time, and then what this does is it describes exactly the same experiment that just starts a little bit later. This is what the translation is doing for us. Now, the scaling that you see here, what I make here is a picture of what happens if you take c equal to 1 divided by 4. So you can see with c equal to 1 divided by 4, what comes out here is f of 4x, and then we get a factor here which is 2. That means because of this factor 2, we get a function that takes a higher value at x equal to 0. You can see the function we start with takes the value 1 for x equal to 0, but this one takes the value 2 because of the factor we have here. And it also gives a much more compressed version of the same one. So in other words, if you look at this operator and you do it with a value of c that is greater than 1, you get a more compressed version of your function, and you get with a higher function value as well. Yes?
Why the dilation operator doesn't do it the same amount? It's 2 times higher, why it's not 2 times squeezed?
This is because here you have the c stated alone, and here you have the square root of c. So you ask why we have a c here and why do we have a square root here? The reason is that we want this operator to preserve the norm on L2. So if you put in a function that has a certain norm in L2, you want the scaled version or the dilated version to have the same norm. And this is what you will see at the problem session. This is what you get because of exactly this factor. But you could choose not to have the square root. Then you just get that the norm of dc acting on function f would not be the same as the norm of f. Then you'd have to correct with that factor in some calculations. So it's just a matter of convenience that here we take it with c, here we take it with square root of c. Now, what happened if you look at c larger than 1? Here you can see I took d equal to 2, and then you can see you get again a function that looks like the one we started with, but you get it somehow more spread out, and you see it does not go up to the value 1 like we had here. It goes up to the value square root of 1 divided by 2 instead. We want to prove some properties of these functions. And what the statement says is that all operators so all the TA and all the EB and all the DC. So when I write it like this, it means no matter how you choose the parameter A, no matter how you choose the parameter B, or no matter how you choose the parameter C, but still C greater than 0 like here. So for all of them, we get the same statements. They are well-defined. They are linear. And they are bounded. So these three properties are something that you have checked many times at the problem session. But there's a fourth point here, and that's the reason that I reminded you about the self-adjoint and unitary operators. It turns out that all operators are unitary. So how can we prove that? So what we'll do is to give the full proofs of these statements for the operators TA. And then at one of the problem sessions, you will prove it for another one of the operators, and then the homework, you'll prove it for the last operator. So we get through all of them at the end. So what we do now is just prove for the operator TA. So we have to prove that the operator is well-defined. And what it means that this operator, that the translation operator is well-defined, means we have to prove that it is actually an operator that goes from L2 of R into L2 of R. So that means we have to prove that if F belongs to L2 of R, then we must show that TA of F also belongs to L2 of R. So the way to do that is to say, what does it mean that TA of F belongs to L2? This means that we have to look at the integral from minus infinity to infinity, and then we take the function value TA F of x, and we take it absolute value to the power 2 dx, and we need to show that this is finite. Now, about the notation, you see here, because this is the first time I introduced the operator, I actually put a bracket around the operator. Sometimes I put it, sometimes I don't put it. I think maybe you will put it the first time you write down the operator, but then already the next time you'll decide that you don't need to put this bracket. So it is up to you if you want to put bracket around the function or not. But we have to show that this is finite. And the only way we can do that is to write down how does our operator act. So what is this TA of F? And this is what the definition tells us. This is F of x minus a. So we have to put that in. So this is the same as the integral from minus infinity to infinity. F of x minus a, absolute value to the power 2 dx. Now what we know is that if you just take the integral of f of x to the power 2, we get something that is finite after integration. Here we have f of x minus a, so what we have to do is somehow to get rid of this a. And the way to do that is to make a change of variable. So what we'll do is to introduce a new variable y equal to x minus a. If we do that, then we get dy equal to dx, and then we get an integral of f of, and then instead of x minus a, we get this is just the y, and then absolute value to the power 2, and instead of dx, we get dy. And the limits are still the same, because if x runs from minus infinity to plus infinity, then also x minus a will run from minus infinity to plus infinity. So the limit is still the same, minus infinity to infinity. So here you can see you're just left with the integral of f of x, or f of y, to the power 2. And the assumption that the function is in L2 means exactly that this integral is finite. So that means at the end of the calculation, we see that TA of f actually belongs to L2. So this is the third part. This is okay. So then the second part is we must show that the operator is well defined, that it is linear. So that means we have to work with TA, and then instead of applying it to the function f, we apply it to a linear combination alpha f plus beta g. So we need to show that the function that comes out here is the same as just alpha times TA of f plus beta times TA of g. But in order to work with this function, we need to calculate what is the value in a point x. And the definition says we need to take the function we're dealing with, which is now alpha f plus beta g. And then what the operator is doing is that it replaces the x by x minus a. But the function alpha f plus beta g evaluated at the point x minus a, this is the same as alpha times f of x minus a plus beta times g of x minus a. And if you look at this, you can see that this is exactly alpha times f of x minus a. This is the same as TA f of x. And then what we have here is beta times g of x minus a, which is the same as TA g of x. So what this shows is that no matter which x you are looking at, then the value of the function TA of alpha f plus beta g is exactly the same as the value of the function alpha TA of f plus beta TA of g. So that means this function is the same as alpha TA of f plus beta TA of g. And what this shows is that the operator TA is linear. Then we need to show that it is bounded. And you know already from the exercises that usually we get that for free when we have showed that the operator is well defined. And this is exactly what happened again here. Because to show that TA is bounded, we need to look at TA of some element f. Now, I actually would like to, instead of just calculating the norm, I would like to calculate it to the power 2. Because if you calculate it to the power 2, we get rid of the square root that is on the norm. So if you look at the norm to the power 2, then by definition, this is the same as the integral from minus infinity to infinity of TAF of x, absolute value to the power 2 dx. So you see, if I did not put this factor of 2 here, then I would have to take the square root of this, and then in all the calculations, we would have to put this square root. So instead of having this square root 5 times after each other, it is much more convenient just to look at the norm to the power 2. But if you look at this, the integral of TAF of x, absolute value to the power 2, this is exactly what we looked at here. From here until here, we showed that this is exactly the same. So this is by the calculation in 1. This is the same as the integral of f of y, absolute value to the power 2, dy, from minus infinity to infinity. And this, again, this is exactly the norm of f to the power 2. So now, after doing this calculation, we can take away the power of 2 here, and we can take away the power of 2 here. So the conclusion is that the norm of TAF is the same as the norm of f, and what this says is that the operator f is bounded. That the operator t is bounded. Actually, you get even more than that it is just bounded. You get that the action of the operator on an element is exactly the same as the norm of the element itself. So this means that the operator is actually what we call an isometry. So this very nice property, you get it for the translation operator, and you will see also that you get it for the later, you get it for the modulation operator, and then, as we discussed just a couple of minutes ago, because of this strange factor, you also get it for the third operator. So this factor makes sure that all three operators have exactly the same property. Now the worst part is missing. We have to show that the operator is unitary. To show that the operator is unitary, we need to look at the definition. It says that the operator composed with its adjoint operator must be the same no matter which order we compose the operators in, and in both cases we need to get the identity. So what this tells us is, if we want to check whether the operator is unitary, we have to calculate the adjoint operator first. So how can we calculate the adjoint operator? This is exactly what we discussed before the break. So let's put that back again. So what it says is we need to look at the inner product of the operator. Now the name of the operator is T with an index A, acting on an F, inner product with G. And then we need to do some manipulations on that, so we somehow get the TA to be moved to the other side, to the G. So we write down what the inner product means. This is the integral from minus infinity to infinity. And then we have TAF of x times the g of x complex conjugated dx. So we have to do some manipulations. So this operator somehow disappears from the f and somehow appears on the g instead. In order to do that, we have again to write down what is TA of f. We always have to go back to the definition of the operator. So TA f of x, this is f of x minus a, and then g of x complex conjugated dx. And how can we proceed from here? Do you have an idea about that? Yeah?
It's a convolution, right? This is a convolution. Really?
This is a convolution, but almost nobody here knows the convolution yet. We are introducing the convolution later, but you know it, but most people here don't know the convolution yet. So, but do you have an idea how to get rid of the a? Because what disturbs us is somehow we would like to have the f alone. That means you would like to have the f of x. We don't have the f of x, we have f of x minus a, so somehow we have to get rid of this. So how can we do that? Elena? You will make a change of variable.
As we did in point 1?
Exactly as we did in part 1, yes. So you say, again, you take a y and you put it equal to x minus a. Then we get again dy equal to dx. So we get the integral, and then f of x minus a, this will then be f of y. Here there's a g of x, but x, if you look at this change of variable, x is equal to y plus the a. So that means we get g of y plus a complex conjugated, and now dy instead of dx. And again, this is the same change of variable. So because here we had the limits going from minus infinity to infinity, even the new variable y will go from minus infinity to infinity. So this is the same. So the question is, do we recognize this? And I claim that we do. This is also a translation operator, now acting on the function g. You can see the translation operator TA acts by subtracting a. Now we get something where we have added the a instead. But this just means that we are looking at the translation operator not with the parameter a anymore, but with the parameter minus a. So what we have here, g of y plus a, this is the same as t with index minus a, applied to g, calculated in the point x. Why did I change to x? I think I should stick to the y, because we had the y here. So let's keep the y, and then still the y. But we have to come back to the inner product, because this is what the conditions say. You see, if you look at the adjoint, you want this inner product to be equal to this inner product. We want to get rid of the t, somehow get it on the other side. So we need to get it back to the form of an inner product. But what we have stated here is exactly an inner product, because you can see that this is exactly the inner product between f and then the operator t minus a acting on g. So you can see what happened at the end is exactly that this operator t of a, we got rid of it, but the price to pay is that on this side we have a t minus a instead. So if we look at the general definition of the adjoint operator, we would say that what comes out by taking this operator and moving to the other side would be t a with a star of g. This is what the definition says. What comes out on the other side, when we have an operator here and we move it to the other side, then the name we get it on the other side is the same, but with a star on it. So by the definition of the adjoint operator, so by this formula 4.13, we know that what comes out here is the same as TA star of G. So what we have actually proved now is that TA star is the same as T minus A. Do you think this is okay? Actually, this is not completely clear, but we have a lemma in the book that tells us that everything is okay. So, you see, it is a little bit dangerous what I'm doing now. I say, just because this is the same as that, then we can conclude that this operator, the two operators, are the same. But we have a lemma that says that if these inner products are the same as these inner products for all choices of the f, then we can be sure that what we have here is the same as what we have here. That means for any element g, t minus a acting on g is the same as ta star acting on g. And this means exactly that the two operators are the same. If you are not completely sure about that, please ask me at the problem session, then I will be happy to go into more details with that. But from the statement here, we can actually conclude that these two operators are exactly the same. So this was the first conclusion we had here. We have calculated the adjoint operator now, but we want to show that our operator is unitary. So I would actually like to know how you think about that. So if you look at the definition, we must show that, you look at it again here, we must show that the operator is unitary, so we have to show that this is satisfied. So we must show that Ta star, Ta is the same as Ta star, and this is equal to the identity. So let me know how you do it. Let's start with, for example, this one. Ta star. How will you show that this is equal to the identity? Is it clear or is it complicated? Or how can we do it? Yes, Lina?
Yeah, I would operate on a function and hope that it will stay as the function itself.
Yes. So you will operate it on a function f. And how will you do that?
We portion-wise first with the Ta with the star and then with the Ta.
Yes. What I mean is you have to evaluate it in a point x to find out which function we're dealing with. So in order to find out what is this function, you have to calculate what is the value in a certain point x. So we have to calculate what is the value in a point x. Before we do that, let's insert what we know about the adjoint operator, because we have shown that the adjoint operator is just t minus a. So what we have here is ta, and then the adjoint operator is t minus a f of x. So now the question is, do you really want to do some calculations, or you will just say this is the same as f of x? Can you see something here where you can just make a picture to tell you that everything is correct, or you really have to do the calculations? Yes?
First,
yes.
One of the operators will move the graph to the right, and the other will move it to the left, and they will move it the same amount, so it will just end up.
Exactly. So what this operator is doing is it takes the function and then it moves it 5 units to this side. But then this is the same translation. This is again a translation by 5, but with a minus. That means it just moves it back again. That means just by looking at, here you have the a, here you have the minus a, you can see that they have to be the identity. So you don't need to do any calculations. So this is f of x. So this is by geometric argument. But of course you think that I like so much epsilons and all these things to make it completely precise. So of course we can also write it down if you want. If you want to act with the operators, then we say Ta acting on this. This means that we have to look at t minus a f, but now we have to evaluate it in x minus a. But to act with the operator t minus a on something means that we have to look at what we have here and then say minus the minus a. So that means at the end we get f of x minus a minus minus a. And then you see exactly, here we are subtracting the a, but here we are adding the f again. So what comes out is f of x. So that means that ta star acting on any function gives exactly the same function. And this means that the operator is the identity. And then what you have to do is look at exactly the same in the opposite way. You do exactly the same again, but now you look at ta star composed with ta, and you say ta star, this is t minus a, and then you compose with ta. So now you see the really short version of the argument. This is translation by minus a, this is translation by a, so they cancel each other, and what comes out is the identity. So this concludes the proof that the operator is actually unitary, as we claimed. So the good news for you today is that the arguments we have given here will be exactly the same arguments when you look at the modulation operator and the dilation operator. So there's nothing new compared to what I've done here. You again have to do the right change of variable, and then everything will be okay. Now, before we stop today, I would like to show you another operator. And this operator is not stated in the book. I will write it in the weekly notes that I sent to you on Friday. And some of you will know the operator already. So we will consider an operator that appears in physics. We will consider the momentum operator. So the Danish word for that is impuls operator. So let me just write it down in the same way as I wrote down the operators we had so far. So the name will be a P, and we want it to be an operator going from L2 of R into L2 of R. And the way we define it is that the action on a function f in L2 should be just a number, and this number is minus the complex unit times a certain constant, which is denoted by h with a slash in the middle, and then we take the derivative of the function. So this h bar, this is just a physical constant. And this is something like 6.28 times 10 to the minus 34. So this is a really small number. So now you have the operator. So do you have any comments about that operator? What do you feel when you see an operator like that? So of course we could start running the same program again. You see what we did here. As mathematicians, oh, I took it away. It was what was stated here. So you know again, the first part is the operator well-defined? Is it bounded? Is it linear? And so on. So what do you think about being well-defined? Yes?
It's imaginary. It's not on real models.
But the operators are going from L2 of R into L2 of R. And L2 of R consists of functions that take complex values. So this is not a problem that we have an I in front of it. They can take complex values. Bjørn?
We need to know if a function in L2 of R differentiated would be in L2 of R. Okay.
So you say, we claim that the operator goes from L2 of R into L2, but nobody says that the derivative of a function is in L2. This is correct, but you even skip the first part because nobody ever says that the function is differentiable. there are many functions in L2 of R that are not differentiable. So for example, we can just look at, actually the easiest function to picture is something that we'll deal with later in the course, a B-spline. This is a function that is in L2, but this function is not differentiable at this point, it's not differentiable here and here. So there are two problems. Or we can formulate it just as one problem. The operator P is not well defined. And the reason is that not all functions in L2 are differentiable. So this is the first problem. Not all functions are differentiable, and even if they are, so even if this derivative exists, it might not belong to L2. This does not mean that we need to give up. This just means that we need to be more careful. This means that maybe it is not a good idea to define this operator on all of L2. So maybe we just look at a certain subspace of L2. So let's do that. So let's define the subspace in such a way that we get rid of the problems. So you know what a mathematician will do? He will just put as many definitions as necessary in order for everything to be well defined. So what we'll do is to say, we consider another space. This is now a space called V. This is the set of functions in L2 of R, where everything goes nice. So this is the set of functions where we don't have this problem. This means this is the set of functions for which this exists. And it also belongs to L2, because this does not come automatically, but let's assume that it does. So this is what we have seen so far. We need to put these two assumptions. Now I'll put a third assumption, because I will do a few calculations in just a few minutes, and then you'll see that we need something more. So I put an extra assumption. Right now you cannot see why I put this assumption, because this is not clear yet. But we put the assumption that f of x goes to 0 for x going to plus minus infinity. So we consider this, and then we consider exactly the same operator. But now we look at P going from the space V into L2 of R, and P of f is the same as before, minus I h slash df dx. Now, this is certainly well defined, because this expression makes sense for all functions in the space V. This is exactly the way we have defined V, and this is also a function that belongs to L2, because this is the way we have defined everything. So this operator is well defined. And actually, it is also linear, because you know, if you want to differentiate a linear combination of functions, you just do it by differentiating each of the functions that appear there. So you know that the differential operator is linear. So it is well defined and linear. So it starts a little bit better now, but we get a new problem. So can anybody tell me what is the problem now? So again, it's something with the p, but what is the problem now? Dario?
I remember we had an example with differential operator which was not bounded. Is the problem?
So you guess that the problem is p is unbounded. That's a very good answer. Let's look at what you are saying. You say we had this exercise, and then the conclusion of this exercise was that the differential operator was unbounded. So you see here, this is this 212 that is stated here. We are looking at the differential operator, and the conclusion is that D is unbounded. Now you see, the conclusion that is stated here is the same as what I'm writing here. Does it mean that we don't have to show anything? Can we take the conclusion from here, or is it just something that we can use as motivation? Bjørn?
Unbounded for functions in L2.
So you say we need to show that it is unbounded for functions in L2. This is completely correct. What we are doing here is we are considering the differential operator acting on the space C1 going into a space of continuous functions. And these spaces, both of them are equipped with the supremum norm. So that means if we are looking with the domain space and the range space and we equip them with the supremum norm, we get an unbounded operator. What we are doing here is different, because you see we are looking at the P from L2 into L2, and then we restrict it to a subspace. This is still in L2, and this is still going into L2. So that means what we are doing here is to speak about the operator, but on the L2 space. That means to show that P is not bounded, we would have to do a new calculation. But at least the argument comes from here. The feeling that something is going wrong, we get it from here. And we could do that, and actually I have an example, but I don't think that I have time to show it to you. At least I will do it on this weekly note I sent to you, so you get the full argument for this. Just for what I want to show now, let's skip that part. Let's just take it for granted that the operator is not bounded. But you know, in physics, people really want to check that operators are self-adjoint. So they claim that P is self-adjoint. So that means they claim that the operator is equal to its adjoint. But this does not make any sense for us at the moment, because we have just shown that the operator is unbounded. And to introduce the adjoint operator, this is something we only do for bounded operators. So at the moment, this does not make sense. Okay, but what does it mean to be self-adjoint? This means that if you look at P acting on F inner product with G, you should be able to do some calculations, and then what comes out at the end should be the same as F, and then we always get P star of G. This is what the definition gives us, but if it is self-adjoint, it means that what comes out at the end is just F inner product with PG. So if we can do some calculations starting from here, and then we end up with this, then we have justified the claim of the physics people. So let's see what happens if you actually do the calculation. This inner product, this is again the integral from minus infinity to infinity, Pf of x times g of x complex conjugated dx. So this is the integral from minus infinity to infinity. We have to put in what P of f is. So P of f is minus I h slash df dx calculated x, g of x, complex conjugated dx. Now again, if we want to get rid of this p, this means we need to get rid of the derivative on the function f. The only way you can do that is to say, here you have a product of two functions. You can do partial integration on this. So what comes out then is a term that says you need to take the integral of this, which is then minus I h slash f of x times the second function, which is just g of x complex conjugated. You look at this going from x equal to minus infinity up to infinity, and then you subtract the integral from minus infinity to infinity, and then you take this integral that you just calculated, minus I h slash f of x, and then you have to differentiate the second function instead. So you get a g prime x complex conjugated dx. This is what partial integration will give you. Now look at the first term. This will actually be 0, because the assumption for f of x is that f of x goes to 0 as x goes to plus minus infinity. So this will more or less kill the second term g of x. This is not completely correct. You need some assumptions also on the function g, but for reasonable functions g, this will automatically be killed because you know that f of x goes to 0 for x going to plus minus infinity. So let's just claim that this is equal to 0. Then what is left is minus, minus, which gives you a plus. So this is the integral from minus infinity to infinity, I h slash f of x, g prime of x, complex conjugated dx. So we want to get it back to something like this. This is our goal, to get something like this at the end. So in order to do that, we would need to have f isolated at the end. And the way to isolate f of x is to put everything else under the bar. That means we leave the f of x as it is here, but what we have here, we need to get it under the bar. So what comes out then is that this is the same as the integral from minus infinity to infinity, f of x, and then the bar of something. And this I h bar, it goes into the bar, but the I goes into as a minus I h bar, and then g prime of x dx. And if you look at this, you can see this is the integral from minus infinity to infinity, f of x, and what you have here under the bar is minus I h bar g prime of x. But this is exactly the action of the operator p on the function g. So this is p of g x complex conjugated dx. And now, if you go back to the inner product, this is exactly the same as the inner product between f p of the g. So that means what you have calculated now is that the adjoint of this operator, the adjoint of the p is the one that you get out on the action of g. So you get that p star is, and what the calculation shows, this is p. But you need to do it like this, because we are not doing this in the framework of mathematics 4, where we are dealing with bounded operators. We are calculating with some operators that are unbounded, but we get something that we could interpret like that the adjoint of this operator is the same as p. So this shows again that the physicists, they are doing something that is not precise mathematics in the sense of mathematics 4, but they know exactly what they are doing, and it is never completely wrong what they are doing. So it makes actually very good sense what they are doing. So I'm not saying anything negative about them. Of course, they have to focus on the physics and just use mathematics as a tool. And what we are showing here is what they are doing is not completely exact, but it is very close to what we are doing here. those of you who would like to have this argument that P is not bounded, please just ask me at the problem session. I'll be happy to show you how we can do that. So let's meet there.